If you have a circuit where there's a certain number of finite inputs that can get fed into some logic gates, assuming no memory or feedback in the system, no matter how complicated, it can always be expressed with Boolean algebra. Now this gets useful when you want to have big complicated circuits of logic gates and represent them with much cleaner, simple set of gates, and they'll yield the same output. We can then figure out the output of the circuits faster, given any input, and it will be easier to manufacture too. This is the second video in the digital electronics playlist. In the previous video, we introduced logic gates and what they do. In this video, I'm going to show you how to go from the logic gate to its Boolean expression. Then I'll show you some fancy Boolean algebra rules that can be used to simplify big complicated circuits and express it with a simpler version. If these videos aren't enough, I'll also offer private tutoring, link in the description from my website. Send me a message and I'll see if I can help you out. So first up here, how do we write the main gates as expressions? An AND gate looks like this. A and B outputs C, and it answers the question, is A and B high? So the output is written in Boolean algebra as this. Looks like a multiplication symbol. You can also write it as AB. It's the same thing, but it's not multiplication like normal maths. It just means and. You can solve questions sort of thinking it as multiplication though. With an AND gate, if you have input A is high and input B is low, the output is 0. Same for the opposite way around. Only 1 when they're both high. And that's the same if you think of it like multiplication here. An OR gate looks like this, and it's written like this. And again, you can sort of get away with using it as addition. So if we have A and B written here, these are all the possible input cases. The output of an OR gate is 1 when either or of these are 1. So those are the outputs for those inputs. And if we take the expression A plus B, I'm going to write it out here, the result of A plus B, rather than looking at the logic gate. If we have 0 plus 0 equals 0. 0 plus 1 is 1. 1 plus 0 is also 1. But the trick, and this is why it's not actually addition, 1 plus 1 is still 1. You can't have a signal that's 2.
Why isn't it possible? It's just not. Why not, you stupid bastard?
It's either 0 or 1. So if you OR together 6 signals, if at least one of them is 1, then the output goes to 1. And for an AND gate, if you take in 6 signals and they're all 1, but then at least one of them goes to 0, all of a sudden the equation looks like 1 times 1 times 1 times 1 times 1 times 0. 1, 2, 3, 4, 5. Yeah, there's 6. That singular 0 made the whole output 0. And if you take multiple, so 6 signals and OR them together, 1, 2, 3, 4, 5, if at least one of them is high, then the output goes to a 1. A NOT gate just flips the input, and we write it with a hat above it or a dash, or you can say not A. Now, if you want to combine gates, you just combine expressions the same way. For example, if you had A and B going into an AND gate, then that output goes into an OR gate with an input C. You do it in 2 steps. First, the output of the AND gate is X, and then finally, the Y gate is Y. So writing this out, X is equal to A and B, Y is equal to X or C. Now we can substitute X in for this. So it's equal to A and B or C. So that's the game. You just label each gate's output as you go, like we did here and like we did here. And you could expand this out and have another gate coming along. You label all of the outputs of each individual gate. And then by the end, you've got one expression that represents the entire circuit, as we do here. When these expressions get big and messy, that's when we can simplify it and delete gates. That's where the fancy rules come in. So clear this. The first rule, if something is already true, ORing it with more stuff doesn't matter. So if I have a signal here and it's 1, and then I have an input A, if I OR these together, the output B is going to see 1 or something, and it's always going to be 1. So the rule here is 1 or A equals B, it just equals 1. The second rule is that if you OR something with itself, A or A, the output of that is just going to equal itself, because if you have signal A equals 1, it's instantly going to be 1, the output, because one of the signals is 1. But then if we have the signal is 0, now they're both 0. And so the output equals 0. So there's only 2 use cases here, and these are the 2. And the output exactly matches the input. So if you have an equation and you see that pop up, you can just simplify that to A. Next is if you OR something with its opposite, that's always true. So if I have a signal A here, and then I pass that through a NOT gate, and I take those two and OR them together, now we have A and not A goes to B. So let's write that out in the equation form. A or not A equals B. If A is 1, not A is 0, and so the output B goes to 1. But then if we have A equals 0, A not is 1, and B is 1. So it doesn't matter what A is, always one of them is going to be 1, so the output is going to be 1. If you AND something with its opposite, that's always false, because an AND gate is only 1 when it sees both inputs are 1. But if you have an A that's 1, this is going to be 0, and vice versa. This is 0, the NOT gate is going to inverse it, and that's going to be 1. You're never going to see 2 1s. So the output of this is always 0. Here's one that simplifies circuits all the time, and it's called absorption. If you have A or A and B, and the circuit looks like this, goes to C or something. If you see that written down, A or A and B, it's always equal to just A. Because if A is 0, this could be 1 because, oh no, it can't be 1. If A is 0, the AND gate will never be 1 because it has to see 2 1s to output a 1. So if this input is fixed to 0, the output is instantly 0 regardless if B is 0 or 1. So then now we have A and the output of this is 0. So this sees 2 zeros and the output is 0, which is equivalent to A. Now if A is 1, it doesn't matter what B is because the input to the OR gate just cares about seeing 1 high signal. So the output is going to be 1 regardless. This here gets absorbed into A and we're just left with that. Let's talk about one of the big ones now. This is called De Morgan's law. It says not A and B is the same as not A or not B. And it also says that not A or B is the same as A naught and B naught. So if you can simplify expressions, you can also flip between different gate types, and sometimes that lets you build the exact same circuit using fewer chips in real life. But if you see anywhere any operation on a signal with a big not above it, either of those two, just know that you can separate that out by taking the not, so the hat part on top, and putting it over your individual inputs, and then just flip the sign. So the OR goes to an AND, and then for this one, you flip the AND into an OR. So let's do an example simplification here. If we have y is a and b or a and not b, we can factor out a just like in normal maths. And that brings us to that equation there. Now b or not b is always 1 because remember if we have a gate here, it's an OR gate, we take this signal and invert it. If b is 0, not b is 1 and vice versa. If b is 1, this is going to be 0. So the OR gate always sees at least 1 high signal and therefore the output is always high. So it's just a times by 1, which is just a. So this whole equation here just simplifies down to y equals a. And if you were to build that in real life and saw this circuit here, you would use all of those gates when you can literally just take the y, that wire, and run it through to the output. Saves you a lot of time, a lot of effort, a lot of money, a lot of speed in your computer too. To verify that you've simplified the circuit correctly, you need to figure out the outputs of the circuit based on all of the inputs using what's called a truth table. You do this for the original circuit and then your new circuit, then you see if the outputs of the truth table match up. If it does, then the circuit's of the same functionality and you simplified it correctly. In the next video, I'll explain how the truth table works and I'll run through this example verifying that it works.